Hello everyone. This is the Newton's second law post-lab. Quite a long one, so buckle yourselves in. The first half of the lab, we varied the force by changing what was on the end of the string and kept the mass constant by moving masses from the cart to the string. And when you graphed the acceleration versus the force, you got a linear graph which did contain 0, 0, and therefore showed that the acceleration is proportional to the force with constant mass. So if you push on something twice as hard, it will accelerate twice as quickly. Pretty much as you might expect. We can, of course, create a y equals mx plus b math model off of this graph. The y variable is the acceleration, and that equals your slope, which theoretically should be 0.6250 for reasons which will become apparent later in this post-lab. Units for the slope come from rise over run. The units of rise are meters per second squared. The units of run are newtons. Since a slope generically tells you how much one variable changes when another variable changes, this slope of 0.6250 meters per second squared per newton tells you that for every additional 1 newton of force, you get an increase in the acceleration of 0.6250 meters per second squared. So it's how much the acceleration increases for an increase in force. Now, if you have your results from the lab, I'd like you to do a little percent error calculation to see how far off you were. You probably weren't more than 1% or 2 off. There's really 2 major reasons for that. The first one is that I calculated the theoretical value, assuming that the cart and the black bar mass were both 500 grams, and they're usually not. And so that would throw things off a bit. The bigger reason is really how we went about balancing out friction and the angle of the track. And the fact that as we moved masses around, we really should have rebalanced for friction pretty much every single time, but I didn't really want you to have to spend that much time doing that. And so we probably underbalanced sometimes and overbalanced other times, and it all kind of came out in the average, but ends up being one of your probably couple of percent errors there. So we have y equals m. The x variable is the force. The y-intercept is 0, which in this case is really just a restatement of Newton's first law. When the net force is 0 newtons, the acceleration is 0 meters per second squared, or vice versa. And again, this is really Newton's first law. So Newton's first law is really a special case of Newton's second law. So this is our specific math model for the first half of the lab. And when you do a multi-variable lab like this one, you usually want to keep track of the other variables. And so in this case, we kept the mass constant. And everybody's constant system mass was around 1.600 kilograms. Maybe a couple more, maybe a couple less, depending on your black bar mass and cart. So you should ideally write your own number in there. Second half of the lab, this is where we varied the mass by putting masses on top of the cart, but kept the force constant by keeping what was hanging off the side on the end of the string the same. When you graphed this, you got this kind of graph, and this shape is not a parabola. It is in fact something called a hyperbola. Now, if you notice from the graph, as the mass gets bigger, the acceleration gets smaller. And this is what we would call an inverse relationship. And so to linearize this graph, we might try to invert the mass. In other words, try to graph acceleration in meters per second squared versus 1 over the mass in 1 over the kilograms. When you did that, you indeed got a linear graph, which went back through 0, 0, very small y-intercept, and therefore the acceleration is proportional to 1 over the mass with constant force. Or you could say this as acceleration is inversely proportional to mass. If you use the word inversely, it means 1 over mass. Now this is a new relationship, first time we've seen it this year thus far. Basically, you have to realize it's the 1 over thing here that makes it a little complex. So if we were to double the amount of mass that we had, and obviously from the first graph, the acceleration would get smaller. How much smaller? Since it's an inverse relationship, if we double the mass, the acceleration would be 1/2 as big. If we tripled the mass, the acceleration would be 1/3 as big. See the inverse there, hopefully? Here's a tough one. What if we halved the mass? Then 1 over 1/2, or the inverse of 1/2, is 2, so twice the acceleration. And then I'm going to do some examples later on that'll kind of confirm this kind of idea. We can create a y equals mx plus b math model out of this straight line graph over here. So the y variable is the acceleration. That equals your slope, and again, you should write yours in here. But the theoretical slope, for reasons which we'll see later, is about 0.980. And the units, rise, meters per second squared, over run, 1 over kilograms. I'm not really going to ask you to interpret this yet, but we can simplify the units a little bit. That line right there in the middle, that horizontal line, means divide. So this is a meter per second squared divided by 1 over a kilogram. But of course, dividing by 1 over a kilogram is the same as multiplying by the reciprocal, kilograms over 1. And so we could write these units as a kilogram meter per second squared. That combination is going to pop up a couple other times here. So if we put that in, right, we now have acceleration equals 0.980 kilogram meters per second squared. The x variable here is not the mass. That's not the linear graph. It's 1 over the mass. Oh, and by the way, we have to do the little percent error calculation and the same sources of error that we had before. So again, putting in the x variable is 1 over the mass. Now the y-intercept here, it goes back through 0, 0, but we have to be a little careful about interpreting it because we don't have a 0, 0 on the original graph. We have it over here. So we have to deal with this 1 over mass thing. And when does 1 over mass approach 0? Well, 1 over something approaches 0 as the number on the bottom, the denominator, if you will, gets really big. What's a really, really big number? Infinity. So we can define this y-intercept to mean that as the mass approaches infinity, that little arrow means approaches if you haven't taken pre-calc yet, as the mass approaches infinity, the acceleration approaches 0 meters per second squared. So in other words, if you kept adding mass onto the card, onto the card, onto the card, and you didn't break it, right, it's going to accelerate less and less and less and less. Essentially, this hyperbola here, the axes act as asymptotes, as you would call them in math class. It gets closer and closer, but never actually reaches it. So this then ends up being our specific math model for the second half of the lab. And this is our constant force that we use during that half of the lab. So we have now done two things. We have shown that the acceleration is proportional to the force with constant mass, and we've shown that the acceleration is proportional to 1 over the mass with constant force. Now those are great, but they only allow you to change one variable at a time. I would like to be able to change both variables and see what happens. And so I'm going to put these two things together. If the acceleration is proportional to the force, and the acceleration is proportional to 1 over the mass, my contention is that acceleration is proportional to the force times 1 over the mass, or force over mass, if you will. Now, this is probably math that you haven't seen before, so I want to show you some examples of this. And if you're in class, you will see me actually demo these examples with a modified Atwood's machine, exactly like we used in the lab. If you're looking at this because you were absent on that day, then you might have to talk to your friends about it, but let's see how it works. So here's case one. Let's say that we doubled the force and doubled the mass at the same time. Well, doubling the force should double the acceleration. Doubling the mass should halve the acceleration. And so if you put that together, those two should cancel, and you should just get the acceleration back that you got to start out with. And if you're in class, I'd actually click on this Newton's second law button here and show you that that actually works. Case two, what if we halved the force and also halved the mass? Well, halving the force would halve the acceleration. Halving the mass would double the acceleration. You multiply that together, they cancel. And so again, you should get back exactly what you started. Case three, what if we halved the force?
Coach G, please come to the
Sorry about that announcement. So what if we halved the force and doubled the mass? Well, 1/2 over 2 is 1/4 of the acceleration. So we'd get a lot less acceleration there because we're cutting the force and cutting the mass. And the last case that I would demo for you in class says that what if we quadruple the force and double the mass? Well, 4 over 2, we would end up doubling the acceleration. So I hope you can see that by multiplying them together, we're still holding the original relationships. We're just now allowing us to change both things at the same time. Again, if you're in class, you'll see that that actually experimentally works. Now, this is great because it's a proportionality, but it'd be even better if it was an equation. In order to switch a proportionality into an equation, we have to do two things. We have to add an equal sign, and we have to throw in an extra little number. This extra little number is what a mathematician would call a constant of proportionality. As you can see there, the definition you would get is the constant value of the ratio of two proportional quantities x and y, usually written y equals kx, where k is the constant of proportionality. I've used a z here because k is used for something else in physics, so I just want to use a z. Now, you may say, what the heck is this? Well, we've actually been doing this all year long. We just haven't called it a constant of proportionality. Remember all the way back at our very first lab, which was a circle lab, and we showed that the circumference was proportional to the diameter. Sorry for that announcement. Back in the circle lab, we showed that the circumference was directly proportional to the diameter of a circle. And that means that if you put them in a ratio, what do you get? Well, you hopefully remember, you get pi. So pi is actually the constant of proportionality between the circumference and the diameter of any circle. Just didn't call it that at the time. So now that we have this nice math model we could use as a predictive tool, the only thing we need to know is, what's z in this case? Is it 3.14, like circumference and diameter, or is it something else? Well, we can figure out what it is by comparing the math model we got in the first half of the lab to our general math model. Now, first of all, let me rewrite it a little bit, which I can do because this is all multiplication, so it's commutative and associative. And now compare this to the math model we got in the first half of the lab. There's our acceleration on the left, there's our force on the right, and that means that z times 1 over m, this part, has got to be the same as the slope of our graph was. If these two equations, which are describing the same thing, are going to both be true, z times 1 over m has got to be this. You might say, okay, great. But remember, in this case, we had a constant mass of roughly 1.6 kilograms. So if we calculate what 1 over our constant mass is, that's 1 over 1.600 kilograms, and we get 0.6250. So 1 over the mass is actually the slope of your graph. And if 1 over the mass is the slope of your graph, then the only thing z can be, to make z times 1 over your mass be that number, is a 1. The world's best constant of proportionality, 1. Now, we do have to be careful about one thing, and that is units. Notice here we have 1 over kilograms here, and we have meters per second squared over newtons. So the only way z can actually be 1 is if the units cancel out. Or, if we do a little cross multiplication, if 1 newton is 1 kilogram meter per second squared. Again, you saw that earlier if you remember. Now, you might say, well, what the heck does this mean? We'll get there. We'll explain it here in just a minute. But do remember that back when I first introduced the Newton to you in the force of gravity lab a couple of units ago, I said that we couldn't really define how big a Newton was. We could only say that it's about 0.22 pounds. And that later we would be able to have enough physics to actually explain why it's 0.22 pounds. And it's not just some randomly chosen thing. And we'll get there in just a couple minutes. So, we have figured out that z must be 1 so long as 1 newton is 1 kilogram meter per second squared. Well, we can confirm this again by comparing the equation we got out of the second half of our lab with the general math model that we have here. If we again rearrange, we have the acceleration on the left, 1 over the mass on the right, and that means z times the force must be the slope of our graph. The only way both of these equations can be true is if z times the force is 0.98 kilogram meters per second squared. And if you look here, you'll notice the force is the slope of the graph. They're exactly the same. And so that means, again, the only way this could work is if z is 1. And if we check out the units, the only way the units work and cancel is if 1 newton is exactly 1 kilogram meter per second squared, exactly as we found in the previous part. So it seems that in both halves of our lab, the only way our specific math models could be true and our general math model could be true is if our wonderful constant of proportionality here is a 1. So if we plug 1 in for z, and this is what I mean by 1 being the world's best constant of proportionality, remember that 1 is the multiplicative identity. If you multiply by 1, you just get the variables back, or you just get the quantity back again. And so we don't even need to remember this 1. I mean, this is way better than pi. Pi, with circumference and diameter, we have to remember is 3.14 so that we can use the equation. But here, this 1 just disappears. So if we solve this for force by multiplying by the mass, we get one of the most important equations in all of physics, an equation that without which we wouldn't be able to understand how things move and why they move the way they do. And this is Newton's second law of motion. And it simply says that the net force, and again, net force, is mass times the resulting acceleration of the object. Now, if you look at this, you'll notice that, again, Newton's first law is just a consequence. It's a special case of Newton's second. If the object isn't accelerating, zero acceleration, we get zero net force, and vice versa. If there's no net force, there's no acceleration. So now what we can do is we can now find, if we can find the net force, force diagrams and those kinds of things as we did in Unit 2, we can then take this and find the acceleration, or vice versa. And our acceleration is linked to all the things we know about uniformly accelerated motion, like the kinematic equations and the graphs and the motion maps. And one other things. You might be able to see now why it's okay to say 1 Newton is 1 kilogram meter per second squared. In fact, when they wanted to define what a Newton was, they used Newton's second law. So 1 Newton is the force required to accelerate a 1 kilogram object at 1 meter per second squared. Again, 1 Newton of force, 1 kilogram of mass accelerated at 1 meter per second squared. The Newton is what is known as a derived unit. Right? They didn't want to have to walk around saying, hey, look, I'm applying this many kilogram meters per second squared to that box. So they gave it a special name. They called it a Newton. And so you have to remember where the Newton came from and what it stands for if you want to work units in problems later. Now, one quick thing I want to try to impress upon you here, if you're not impressed enough by this whole process, is that this is really science. I mean, we're really doing something kind of impressive here. We did this whole 2-day lab with 3 variables. And then this post-lab, we were using some new math and shoving these 2 things together, and we come up with one really tight, precise, relatively simple equation to describe the relationship between net force, mass, and acceleration. So hopefully you see here that this is really kind of a pretty thing, and we're going to apply it here as we go throughout the unit. I hope you enjoyed it as much as I have.